Hi, welcome to the Dutch landscape, lesson number 3. In previous lessons, we've discussed the geological timescale and some building blocks of a landscape. And today, I want to discuss with you these um, bullet points, so to speak. Geologically speaking, the Dutch landscapes are very young. They are basically all from the most recent geological period, and around 90% of all the Dutch landscapes is naturally formed in the last 200,000 or so years. Now, why do I say around 90%? Partly because I'm not entirely sure on that particular number, but because I don't know how large a percentage South Limburg is from the Netherlands. I'm guessing about 10%, but it could be less. It's probably less. But you could say that everything in the Netherlands is formed in the last 200,000 years, except for South Limburg and, of course, the overseas territories, Bonaire, Saba, St. Eustatius, the islands, the tropical islands that are part of the Dutch kingdom. Now, we'll discuss today why that is. We already discussed this in the introductory lesson because, the Netherlands is the drain of Europe and everything flows to us and we're sinking. So everything that you see has been deposited quite recently. And all the old stuff that happened a long time ago, that's buried deep under new sediment. And I want to discuss with you the natural and human processes that were involved in the various stages of landscaping. And I can already tell you that today our subject is the Pleistocene, and there will be no human processes involved whatsoever. We will be talking entirely natural processes today. And I want to focus on the sequence of events and the causal chains that tied together the landscape that I will discuss. So we'll go chronologically, start a long time ago, relatively long because geologically 200,000 years isn't that much, and then we'll step it up next lesson to the Holocene. Today, Pleistocene. What do I mean by Pleistocene? This was an exercise from your homework booklet on the geological timescale, and we've discussed this in previous lessons too. If you haven't done the assignment yet, I suggest you pause the video and do it now. Take a couple of minutes, just pause the video, and then do the assignment. That's W3, W4 will stop when we'll do this at the end of the video. So start with W3, do it now, take a minute, and pause the video, and then come back to me. Okay, so we're back. Assuming you've paused the video and did the assignment, the geological timescale, they start with the Cenozoic, which is the period of the new life. It starts 65 million years ago. The asteroid hit the Earth. The dinosaurs are dying or dead. And mammals seize the moment to start breeding like idiots and take over the world. Muhaha! That's where we come from. Now, the Cenozoic can be split into two distinct periods. The biggest by far is the Tertiary system, and this starts 65 million years ago. The other one is where we live now, is called the Quaternary system, and it starts 2.5 million years ago. Now, the Quaternary can also be split in two, and then you've got the Pleistocene, and the Pleistocene starts 2.5 million years ago, and everything that is older than, let's say, 400,000 years or so, 380, is called the pre-glacial period. Now, this is not actually true. There's been quite a lot of glacial periods, ice ages, during the Quaternary system, during the Pleistocene. And just to make it easy for you, just like we are not going to discuss the Hadean and the Arcadian, we're just going to call everything before the Cambrian the Precambrian. We're going to call everything before the Saale Ice Age the pre-glacial period, even though there are glacials in that period. We're going to call it pre-glacial. So with pre-glacial, I'm going to refer to everything before the Saale Ice Age. And the Saale Ice Age was important. It was 150,000 to 100,000 years before present. or so, roughly, take it. And then there is also the Weichsel Ice Age, which in your book is erroneously called the post-glacial period. In the book, they use everything after Saale Ice Age. They call it the post-glacial, even though it's a interglacial, glacial, interglacial. All right? So the book makes a mistake or tries to make it easier for you, even though it isn't. So what I want you to remember from this is that there are two glacial periods that are very important for the Netherlands. It's the Saale Ice Age and it's the Weichsel Ice Age. And the Weichsel Ice Age, it stops 11,700 years before present. That is before present, not before Christ. Okay? You can also say roughly around 9,000 years before Christ is fine by me. But I'm going to use BP before present. So we're going to call everything before the Saale Ice Age preglacial. We're going to call the Saale Ice Age the period from 150,000 to 100,000 before present. Then there was an intermission, no ice age for a while. And then there was the Weichsel Ice Age. And the interglacial over here and the Weichsel Ice Age together are named the post-glacial period in the book, which makes absolutely no sense to me at all. And then there is the Holocene, that is the last 10,000 years of the Earth's history or so, and we'll discuss that next lesson. So everything that happens in the Holocene is not subject today. We'll be discussing this bit. So we're going through 2.5 million years, and we're going to stop at 10,000 years before present. All right? Good. Here we go. I hope everybody realizes that the Holocene is nothing more than a period between ice ages. It just happens to be the most recent one. And the Holocene, we've seen, is when people become awesome. They start living in cities together and they specialize. And, there's enough to eat for everybody. So we become increasingly more complex. And, we go to the moon eventually. We have enlightenment, etc. So the Holocene is everything you've learned in history class, except maybe, in the Brugklas, the prehistory that takes place here. Maybe even here a little bit, maybe one or two things. But all the rest of the history is this. Okay? Now, here you see a graph of the temperature of the last 420,000 years. And you can see the interglacials. This is the Holocene. Then this is the Weichsel Ice Age. This is another interglacial. It was called the Amian. You don't have to remember that. And then this is the Saale Ice Age. All the way over here. Then there's another interglacial. You don't have to know the name. Then there is another cold period. You don't have to know the name. Interglacial. So this has been going on for a long time. Now, a good question is, how do we know all this? Well, what clever scientists do is they go to a place where there's been ice for a very long time. They go all the way to Antarctica, and they start drilling in these huge ice sheets that are over, kilometers thick. There's roughly around 3 kilometers of ice on Antarctica, and there's also a very large glacier on Greenland. And they drill in the ice, and within the ice, gases from the atmosphere at the time of the precipitation of that snow that eventually led to the glacier has been caught in the ice. So they can measure the amount of CO2 in the ice cores, and then they can calculate from that what it does to the temperature. So what we know is that right now we're at not an all-time high, by the way, but we're pretty high when it comes to CO2. By the way, the most recent one is not even on it. It stops at the year 0, which is the birth of Christ. So we're at 2000. We're over here somewhere, and we're peaking. We're over 400. So we're not even on the chart right now. Okay? By the way, this is 0 before present. So it's not when Jesus was born. This is just erroneous. We're very, very high. And, when they start looking back in the ice cores, they see that Over here, the CO2 was very low. Then the CO2 was high. Then the CO2 was low. Then the CO2 was high for a long time. And then the CO2 was low, high, low, high. The CO2 levels haven't been very stable these last couple of years. And if you don't like the cold, like me, I can get used to these, mild winters that we've experienced lately. December was the warmest December ever measured. It was as warm as the average month of April, which is weird. And now I'm getting a message. It's very weird to have that happening, but I can get used to it. I was New Year's Day, I was running with only a shirt on because it was 12 degrees centigrade outside. Crazy, right? So I can get used to that. I could move to the south of France and enjoy that every day. But normally the average is roughly around here if we calculate everything. So roughly around 260, 65 parts per million. And that hasn't been stable. And now we're at an all-time high somewhere over here, which is not on this chart, which is weird. But okay. So we know that CO2 is the temperature of is a proxy for the temperature of the Earth. The more CO2, the more greenhouse effect, the warmer it gets. The less CO2, less greenhouse effect, the warmth of the Earth does not get caught in the atmosphere, starts to become cool, and so we can calculate these graphs: warm, cold, etc. And this has been going on for the entirety of the Quaternary system. So this is the Netherlands in the pre-glacial setup. So we're over here somewhere, okay? Right. Now, this is the low, this is the ocean, this is low, and all the water from the continents wants to go to the lowest point, and it flows this way. And they drew the Netherlands over here, and this is the modern Scheldt, and this is the modern Meuse, and this is the modern Rhine, and this is the modern Eems, and this is the modern Hamburg. I don't know which one this is. This is the Eems. What's Elbe? Of course, German river. Okay, and by then they were probably flowing this way, and they were probably flowing that way, and this one is flowing this way, that way, this way. All the rivers flow this way, and what do rivers do? They deposit sediment. They deposit sediment it's called an alluvial fan, in a fan way. So these are the Alps, and the water flows, and it comes to the lowlands, and sometimes the river flows over here, and it deposits over here every time it flows over, and then for some reason the river starts flowing over here, and then it deposits some sediment over there, and then the river comes this way. And these are wild rivers. There are no levees or dikes, and people haven't done anything, so the rivers are free to do whatever they want for hundreds and thousands of years. So you see this happening. This is a river flow, and then it deposits some stuff over here, gravel and cross beds, and the massive gravel is over here because here the water flows very quickly and takes everything, and only the large boulders, they come down. And then over here, the river starts flowing a little less quickly, and the gravel flows down. And then over here, the river doesn't flow as quickly anymore, and everything falls down, even the smallest particles. And this happened in the whole of the Netherlands for hundreds and thousands of years. Here you see a beautiful picture of a beautiful alluvial fan somewhere in the Arctic, and you can see the gravel bits. These are big gravel bits, and then here's some mid-level gravel bits, and then the smallest gravel bits are over here. Now this was the Netherlands for a long period of time. All of this was alluvial fan. Okay, and I'm gonna show you a cross-section of the Netherlands. This is the east, this is the west, and along this line I've made a cross-section, and it looks something like this. This is the east, which is slightly higher. This is the ocean, all the way in the west. And this is the deposition of the prehistoric Rhine and Meuse flow, because this is all put down because the Netherlands and large parts of Germany are Europe's drain. The pre-glacial sands and clays are called the alluvial fans. This is our basis. This is where we're going to start looking at the Dutch landscape. This is our starting point. Slightly higher in the east because it's farther away from the ocean, low in the ocean. This is the North Sea, and I'm getting another message, and I'm going to put my phone off because it's very, very annoying. Go away. No. Go away. Yes. Thank you. All right. So, alluvial fan, right? Now, what happens in an ice age is that the water evaporates and then comes down in the form of snow, and then the snow doesn't melt, and the rivers don't flow back to the sea. So what do you get when you do have a little tiny bit of evaporation and no flow back to the sea? The seas dry up and glaciers grow because it doesn't melt as much as it used to do. And here we go. Sea starts to recede. The Netherlands becomes a lot bigger. We could walk all the way up to England. Yay! We didn't have to use Stena-line, even though free fish, Stena-line. Free salmon, free eel. Good meals on the Stena-line boats. If you ever go to England, take the night boat and eat yourself nauseous on the free fish. The Netherlands was bigger, and it was all pre-glacial sand and clay. And then land ice started to bulldozer its way all the way from Scandinavia all the way down to the Netherlands. And what does land ice do when it comes down from Scandinavia? It's like a bulldozer. It pushes the sediment that's in front of it, and it pushes it all the way up to form these hills. And they used to be pretty high. These hills used to be 100, 150 meters or so high. And now, of course, it's 150,000 years ago, erosion has taken the tops off already, and they're not as high anymore. But I think the Grebbeberg is still roughly around 100 meters high. These are pretty, big hills. And these land ice sheets, they were pretty massive. They were up to 1 kilometer thick in Germany, and in the Netherlands, they were up to 150 meters of ice. All right? These were pretty big things. Now, the reason that this is not it's a crude, but not a very accurate depiction of what's going on with the land ice, I'll show you in a second. So don't take this movement all too literally. It's a figurative demonstration of what a push moraine is and what a land ice sheet does. And I'll show you in a second why. Now, what land ice also did was they formed basins. And a basin is nothing more than a fancy name for a low-lying area anywhere. Okay, the North Sea is a big basin by itself. And these land ice sheets, what they did was they came through riverbeds and they took the path of least resistance, and this is why they pushed down the ground there a little bit, and they in some cases scraped it out to form these push moraines a little bit. And so the places where the ice lobes were, they are called glacial basins, and I'll show you a map in a couple of minutes to show you exactly what I mean by this. This is kind of a weird depiction, which is also a reason why the ice sheet coming in from this way in one straight line, etc., is not completely accurate and correct. I'll correct that in a second, all right? Don't worry about it. Don't worry about it now. Also, what ice does is it's very, very heavy. 150 meters of ice on top of your head will squash you down. And it also squashes sediment. And these sediments, they were made up of clays and of sands and in some cases pebbles. And the glacier, they took a lot of stones with them that were pushed underneath the glacier. And all of these were ground up into what is known as boulder loam. And boulder loam is a very, very, very resistant, tough layer of ground together sand and clays and stones and pebbles, and water doesn't get through very well. And boulder loam is a mixture of that. The book describes it as a mixture of boulders ground into loam and stones that were still whole. So there's a lot of rocks in here as well. Okay, so the glacier comes down, the land ice sheet comes down, and it pushes up a hill called the push moraine. It digs out a basin called the glacial basin, and it squashes together what was already there, combined with what it brought itself, to form boulder loam. So three things are formed by land ice in the Netherlands. Now the reason, okay, I've got actually a pretty good movie, a guy on the internet with a funny looking face, but not by half as ridiculous as the way I look. He shows you exactly how a push moraine is formed, and I thought it was a good, accurate way to describe how a push moraine works.
Hi guys, I'm Richard from Moraine Marauders Limited, and I'm going to show you how a moraine is formed, but in miniature. This glass dish here represents Cheshire and Shropshire, and my fist represents the glacier. As the glacier came down from the north and from the Irish Sea, it scrapes along the sediment, and it creates like a front in front of the glacier, as can be seen now. This is basically what a moraine is. The sediment that's being pushed along by the glacier. This thing can happen as it goes back and forth, if it retreats and then it comes back and then pushes forward again. This is when you have recessional moraines, and you'll have layers of moraines, as you can see, as the glacier falls back and then advances again, as such.
Okay, so that's really a very accurate and apt description of what goes on when a push moraine is formed. And what I like about this clip is that he's also immediately telling you that a glacier, in this case his fist, will not move in one singular direction at a singular speed all the way over here, but it will, come forward and backward and then forward and backward again and then backward, and then maybe in a particularly heavy sequence of winters it will ground all the way over there and, push everything that it's just pushed up here further and then come back and then etc. So bear in mind that land ice doesn't move, in one singular motion and in one singular line. It always follows the path of least resistance. So here's an ice sheet, and here's land, and here's the push moraine. And what is very clear is that apparently for some reason over here there is more resistance. Over there, apparently there's more resistance. Over here there's a little more resistance. And there was least resistance over here, which is why the ice sheet can come this way and this way. Now, what could be a reason for less resistance? Well, old river valleys or places where there is clean shaved bedrock, those places make it very easy for ice to slide over. If you have a place where there is a lot of tough stuff in the ground, like boulder loam, and the ice comes, and it is not as easy to push the boulder loam up as coarse gravel or slick bedrock, like rocks that aren't too spiky or gravelly or whatever, the ice is more likely to come that way. And also, the ice doesn't move in one singular direction. It goes back and forth as temperatures drop or rise, or as precipitation, as there is more precipitation and snow or less. So when we look at, for example, this area on a map in the area of Nijmegen, close to where my brother lives, you can immediately see where the ice has found some resistance and where it hasn't. Now here, this is interesting. This is where, for example, a little meltwater lake broke through and flowed, so there is no more push moraine over here. So here was an ice lobe, here was an ice lobe, and then over there was probably an ice lobe, and the glacier was coming from this direction. and then there was a lot of resistance over here, and there was some resistance over there, and there was some resistance over here, and this was pretty much the ultimate lobe that pushed up. This is the terminal moraine, and it was simply not possible to go further because of the temperatures and because if there was something in the ground. So this one can still be seen. That was an ice lobe. This one was an ice lobe as well. So bear in mind that it doesn't move forward in one steady motion, and sometimes it takes 2 steps forward, then it's a particularly mild winter and it recedes 1 step, and then it was for 3 years in a row super cold, and then it comes forward, and then it was 4 extremely hot summers, and a lot of stuff melted down and it went back again, and then it went forward, etc. So depending on variations in summer and winter average temperatures and precipitation and surface resistance, etc., these things came forward and backward. Okay, now we're fully in the Saalian, and this is what the Netherlands looked like in the Saalian Ice Age. We're not really sure about exactly how these Ice Age lobes either connected or not, but we do know that these rivers, they move this way now, and over here, and over there, you can see the push moraines. The Dutch word for push moraines is stuwwallen. And this was a place where an ice lobe, sort of a tongue shape, which is why they're called glacial basins, glaciale bekkens of tongbekkens. So any of you like the tongue, then remember that it's also a glacial form, tongbekken. So there was an ice lobe over here, and it pushed up moraines over there, which are now buried in the North Sea. And there was one over here, and there is one over there in Twente. And this is the most famous one and the biggest one. This is the Veluwe. And the one we've just been looking at was this one, Beek-Uberge. Okay. So, what do we remember? What do we have to remember from the Saalian? Well, the Saalian is an ice age. It is the most frosty ice age in recent history, and it shapes the Netherlands in one way. What way? Okay. Up until the Han line, Haarlem, Utrecht, Nijmegen, the Netherlands was covered in land ice. What does land ice do? It shapes push moraines and glacial basins. What else does it do? It grinds the alluvial fan down into boulder loam. So in this case, here we can find some boulder loam, we can find some push moraines, we can find some glacial basins. In the south of the Han line, no ice, ergo no push moraines, no boulder loam, no glacial basins. What else did the ice do? Well, they brought rocks with them from the mountains where it had initially started. Those are called glacial erratics because eventually this ice melts and drops out the rocks. So when you're on the Veluwe and you find, these glacial erratics, zwerfkeien, of which we have one in school, Karel, the granite, that rock should not be here. It comes all the way from Scandinavia somewhere. Sweden, Norway. Those mountains gave birth to the glacier that would eventually become this big, massive ice sheet. And there are scientists out there that study the particular rocks that are found somewhere and then can retrace all the way the glacier has pushed that rock to get here. So there are actually guys out there matching glacial erratics with mountains based on mineral composition of the rock, type of granite, etc., and matching those to see which one came where. Okay, if you ever think that you need to find a new hobby, then there's that. Okay, so Saalian Ice Age is over. New warm period called the Amian, which you don't have to remember, but all this ice melts. The North Sea fills up again with water. and happy peppy, everybody's living under relatively normal conditions, but not for long, because after about 20,000 years or so, a new ice age is on its way. However, it's not as frosty as the Saalian ice age. It's pretty cold, but it's not as cold anymore. And the Netherlands has a tundra climate with wind directions coming from the northwest. Northwest. Now, this is what it must have looked like: an endless sea of grass all the way back to England. The North Sea is all the way over here. The Netherlands is a lot bigger. And it's all grass, and there is, moose and woolly mammoths and saber-toothed tigers and woolly rhinos, and they're grazing out there. And there's a lovely picture of a mammoth in your book. And there's the Cro-Magnon guy on page 98 of your book, training a wolf. And that's how they lived. And more on this particular setup later when we discuss Doggerland during the Holocene, because Doggerland, I find it interesting that Doggerland might have been the story of Atlantis is actual. What happened on Doggerland might have given birth to the stories of Atlantis. But more on that when we discuss the Holocene. Anyway, during the Weichsel Ice Age, we had an endless tundra of grass. There was no land ice cover in the Netherlands. And I have a question. I see all these rivers flow this way now. Whereas in the pre-glacial period, they flowed all the way up north to the sea. Remember? Now, why do they bend? Well, it's obvious. The river cannot flow north anymore because there is all these big hills now of 100-meter high, and the rivers cannot break through. There's one river that breaks through. It's called the IJssel, and it comes in this way. It cuts through this Tongbekken and then flows into the sea over there. So it's this one. It's the River IJssel. And what's really crazy about the River IJssel is that it actually flows a little bit back east, even though east is higher. So it actually flows a little higher to connect to the Tongbekken and then come this way. But these rivers now bend this way, all because of the Hun line and the hills that have formed during the Saale Ice Age. Okay, so this is our setup that we got from the Saale Ice Age. We've got a push moraine over here. Some erosion has gone on, so a little bit, and there is some glacial basin which is filled up. Let's say this is the IJssel basin and this is the Veluwe. Let's make it easy. And then there is a large portion of the Netherlands covered in boulderland. Now in the Weichsel Ice Age, the Netherlands is big again. There is no North Sea, and the dominant wind direction is this way. The North Sea is all the way over here. Okay, now the North Sea is over there, but now it's all the way over there. And the dominant wind direction is this way. So what happens is all the loose grains of sand and silts and gravel that is in the North Sea, it dries up and it gets blown over the rest of Europe. And this is not just the Netherlands. This is the entirety of the German low plains of northern Germany, all the way up to Poland even. These particles get picked up and they're blown over the rest of Europe. Now, cover sands, they cannot be blown up as high in the atmosphere as the lightest particles. Every time we have a dust storm from the Sahara, the people who are reporting on it make a big mistake, and they say in calling it a sandstorm. Now, it's not a sandstorm, it's a dust storm. Sand has a grain size that is large enough to be picked up by the wind, but not large enough to be, blown up really high into the atmosphere. It just doesn't happen. It comes up about, in a good sandstorm, it can, saltate up at maximum, I think, about 2 meters. If a camel stands up, his head will always be above the sand. Now, it doesn't protect him from the dust, because dust is very, very, very small particles. In your book, it's called lus as well. And lus is just dried up clays. It's silt, essentially, and they have very small particles, and they can be blown up miles into the atmosphere. So every time during the summertime, when the southern winds have blown a large part of the Sahara over northern Europe, we are experiencing a dust storm, and these, I have to wash my car because I can't see. So lus, and which is silt, dried up clays, it comes up high in the atmosphere, and cover sands doesn't. It just comes up 2 meters or so, and it gets blown over the entirety of the Netherlands. So the boulderloam gets buried under a large layer of sand. Now, all of this is buried under a large layer of sand. It's been covered. All right? Everything gets covered in cover sands. This is what happens during the Weichsel Ice Age. The setup for the Netherlands at the beginning of the Holocene is a receded sea, the Netherlands covered in cover sands, with a push moraine somewhere, some glacial basins, and some boulderloam with several meters of sand on top of it. So what's the legacy of the land ice? This is the name of the section in your book. Well, the legacy of the land ice is in terms of soil components. Sand everywhere. The Netherlands is covered in sand. Sand, sand, sand. All right? Lus, but only in South Limburg. It's the only place in the Netherlands that gets some lus. All right? It only falls down on the higher bits of the Netherlands. Let's say above 200 meters of sea level. So the Ardennes, the higher parts of the Eifel, and South Limburg as well. Okay, there is some boulderloam in the Netherlands as a soil component, but it's only where the thick packs of ice have crushed the alluvial fan together with rocks. Nowadays, these boulderloam hills can be found on Texel, Wieringen, Gaaseland, Drenthe, and they are now buried by the cover sand, so you have to drill before you get into the boulderloam. Now, obviously, boulders, the glacial erratics that have been discussed. In terms of relief, in terms of differences in altitude, there are push moraines, which are already largely eroded, and there are glacial basins, which are already largely filled up with new sediments. All right? This is an important map because it shows you two important lines. The Han line we've discussed, Haarlem, Utrecht, Nijmegen. The NUP plus 1 meter line will be discussed during the Holocene lecture. Okay, some questions that I could ask you. Name 2 types of glacial deposits. Okay, what does glacial bring? Explain why it's impossible to find any glacial shapes or deposits near Eindhoven. Remember the Han line, this is where the ice got, not further. So no glacial shapes or deposits near Eindhoven because the ice never went there. Which part of the Netherlands has no visible legacy of the ice? Well, this part. No ice. Okay? Now, I could also show you an altitude map of the Netherlands, and I could ask you, where are the basins? Now, hopefully, you can see that this bit is a lot lower, and this bit is also a lot lower than the surroundings. So this is high, the highest. This is low, and my battery is low as well. Close. And then there is this tongue-shaped basin over here. There's a tongue-shaped basin over here. And the push moraines are located around these basins. The Lus is only located over there. Is this a push moraine? Now, you are very, very stupid if you thought it was a push moraine. You are stupid. If you thought that this was a push moraine, you are just stupid. Stupid, 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 stupid. It's not. All right, ice never got there. All right, now here's a map in Dutch of push moraines and glacial basins. Again, the basin over here, push moraine over there, and here we have some boulder loam covered with younger deposits. Oh, I'm getting tired. Now, I'm not gonna bother you with eskers and tunnel valleys, but the Urstroomdal van de Maas en de Rijn, Vecht en de Hunze, these, the Rhine and the Meuse, so this is the Urstroomdal, the way the rivers used to flow before these hills were put down. Okay, Dutch term, Duststorm. Push moraine is a stuwwal, and boulder loam is called keileem. So in case you pick geography for the next years and you won't get it in English, these are some terms that you should know. Okay, so as promised, W4, deposits and transport mechanism. This should be easy now. So take, again, a couple of minutes, pause the video, do the exercise, and then check if you got it right. Super easy. Deposits and transport mechanisms of the Pleistocene. All right, here we go. Assuming you stopped the video and did the exercise, here we go. The alluvial fan is the oldest one. It was put down in the pre-glacial period, and it was put down by liquid water. And what is the alluvial fan? Well, they're deposits of sandy clays. Then boulder loam, which was put down during the Saale Ice Age, and it was crushed by land ice. All right, crushed boulders mixed with stones in sand and clays and everything got crushed together to form loam. Also put down during the Saale Ice Age, glacial basins. It was formed by land ice, and there are large-scale depressions ground out by ice lobes. And of course, my friend, the push moraine, formed by land ice, and they're approximately 100 meters high, and there are hills made of sand and small pebbles and unsorted material that was pushed up by the land ice. Then there are some postglacial deposits, both transported by the wind, the very, very, very fine grains of dried out clays called silt, and that's been put down only in southern Limburg. It's called lus. And the cover sands, they were put down everywhere, and they are called, that was coarse sand put down by wind. All right, that was it for the Pleistocene. Next lesson, we'll focus on Holocene, and I'll explain to you why the 1 meter plus NAP line in this map is so very important for the Dutch landscapes.